Good evening, everyone. Welcome to CodeRally 5.0, organized by the IEEE Computer Society Student Branch Chapter of IIT. We are starting with an exciting workshop on tips and tricks for competitive programming, the final in a series of 6 engaging workshops. I'm Pasindu Wijesena, and I'm thrilled to be here with you all today. Today's session focuses on tips and tricks for competitive programming, where you will learn strategies and methods that will benefit you beyond this workshop. And just a quick reminder about our swag challenge. Share your insights from this session on LinkedIn using the hashtag displayed on the screen. The most insightful post will win exclusive swag in the next session. We'll reveal the winner of the previous session at today's workshop. Your active participation is key to gaining more knowledge and making the workshop enriching for everyone. Please scan the QR code on the screen to submit your questions and share your thoughts. We'll have a dedicated Q&A session later. Now, let's give a warm welcome to our speaker, Mr. Pasindu Wijesena, Vice President of Engineering at Surge Global. He will be guiding us throughout this workshop. We are truly grateful for your presence here today and looking forward to the insight you will be sharing with us.
All right, thank you very much for the introduction. Hey everyone, I hope you all are having a great weekend. And so, like Pasindu mentioned, this is the last of the series of a couple of sessions that we had, where you initially started with learning what competitive programming is, and then dive into different algorithms, data structures, and mechanisms that you can use in competitive programming competitions, as well as in general problem solving. And during this session, what I'm targeting to teach you guys is how you can get better with competitive programming. Now, let me start by sharing my screen. Right, I hope you can see my screen. And so this session is also going to be an interactive session where I will be asking a couple of questions and we will talk with each other and try to go forward. And so for this, I ask you guys to reply to me for any of the questions that I asked through the chat, or you can unmute yourselves and talk. Right, let's jump in. So I'm Pasindu Wijesena, VP of Engineering at Surge Global. I'm also the co-founder at the team. And for this program's context, so I have some exposure to competitive programming. I started back in 2012, so it's been around 12 years right now. And I was a competitor. My last competition was in 2021. So it's been a couple of years since I last competed, but I've been involved in problem setting at competitive programming competitions. So I hope to share some of the insights that I learned along the way, so you'll be able to get better at competitive programming. So as a refresher to what you initially had into like what competitive programming is, and for us to be able to really digest competitive programming and learn how we can get better, let's start with the problem. So this is a number sequence, and I want you guys to tell me what number comes next. So you can type the answers on the chat box. All right, we have answers coming up. And guys, when you are sending the messages, if you can please share it so that everyone can see. So everybody knows what you're talking about. Right. So in this case, 19. What could it be 19? No, really, it's 21. All of you guys are right. So this is a common sequence that that's involved in a lot of computer science textbooks and also in maths. So this is the Fibonacci sequence where a term is built by the summation of the previous two terms. And so this is like we can represent this sequence in this through this recurrence relationship where the nth term is defined by the summation of the previous two terms. And also to define this, we will also need some base terms. So in our case, we have the first and second terms being one. And then thereafter, we can use this recurrent relationship to determine whatever the nth term is. Right. So this is a calculation or an equation that allows us to figure out, given an n, what the n Fibonacci number is. Right. So what is the 21st Fibonacci number? Can you guys tell? Rather than the answer, like how would you have to figure, like what's the way of computing the 21st Fibonacci number? What do you think? What do you have to do? You can type on chat box again. Wait a minute and continue. What's the approach? So in order to compute the 21st Fibonacci number, we need to compute the first 20 Fibonacci numbers because based on our recurrent relationship, in order to compute the 21st, we need to know 20th and the 19th, right? So if you write up the first 20 Fibonacci numbers, and then you can figure out what the 21st one is, right? In our case, this is 10,946. Cool. Now, if you look at how you had to come up with this answer, right? We can write it into an algorithm like this. So let's say we have two variables, T1 and T2. In this case, we initialize those two with 1, right? As the initial values. And then we are going to repeat 19 times by which at the end of this loop, T1 and T2 are going to contain the 21st Fibonacci number. So at each iteration, what we are going to do is we have this temporary variable where we set the summation of the previous two Fibonacci numbers, T1 and T2, into X. And then we do a swap operation where we move the value we have stored in T2 to T1 and then store Tx in T2, right? So this is an algorithm that would allow us to, let's say, given an n here instead of the 21st, you can repeat n minus 2 times in this loop. And at the end, you can output the value of T2, which is going to give you the n Fibonacci number. Right. So what's competitive programming? Competitive programming is competitive programming competitions rather. So in competitions, you get questions similar to what we just saw, but they could be far complicated or far easier, where you have to come up with creative algorithms that can solve the problem, and then you need to express those algorithms as computer code. And during the competitions, what usually happens is when you write this code and then you need to submit them, and a grader system is going to evaluate your code by testing it against some sample test cases. And so then you're going to get some score. Now, in competitive programming competitions, there's something in addition to just coming up with algorithms and submitting your computer code. So whatever the algorithms that you come up have to be correct, and they need to be fast enough. they need to be memory efficient. So whatever the program you write, let's say if it's correct, you can't take you don't have an unbounded time to execute it, right? So for example, if we used this algorithm where we had a loop, uh, yeah, where we had this loop and we wanted to compute the 10 to the power 20th Fibonacci number, the algorithm, like if you were to write a program, it will take forever, as in it will take years to compute. And so whatever the algorithm that you come up with and then you turn into code, it needs to be fast enough. And also it needs to be memory efficient. So there's going to be bounded memory available to you when the gradie is executing your program. So your program should come up with the result without exceeding the given memory limits. So these three things should be there in the programs that you submit, right? And let's have a brief look at what a correct algorithm is. So when I say a correct algorithm in the context of competitive programming competitions, what correctness is that your algorithm and in the end the program that you write should be able to spit out the correct answer for any input in the expected input range. So that is in the CP competitions, in the problems that you get, you usually get a set of constraints. So for example, in here, we have been asked to compute the nth Fibonacci number under the constraints that n is going to be between 1 and 10 to the power 9, right? So it is okay if your algorithm is going to fail in computing the 10 to the power 9 plus 1 Fibonacci number or the 0th Fibonacci number, because as long as you are correct during this range, that's enough. So that's the boundary that you have to look up or consider when you're coming up with the solution. That is the algorithm that you want to solve this problem for, right? And what's a fast enough algorithm? So we talked a bit about this one. So your program must terminate within some specified time limits. So if you take any programming competition, you usually get a time limit together with the problem specification. So again, in this example, it's 1 second. And we need to be able to compute up to the 10 to the power 9, that is 1 billion Fibonacci number within a single second. So if your program is going to fail in computing this result within a single second, it's going to fail. So you need to come up with an algorithm that's fast enough to be able to compute this result within a second. And the third property is your algorithm, and in the end, the program that comes out of it needs to be memory efficient. So there's going to be bounded memory. So we have another small adjustment to the problem now. Like instead of computing a single Fibonacci number, now we've been asked to compute Q Fibonacci numbers for like each of the Qi query. So like we have a set of queries Q, and for each Qi element in the array Q, we need to compute the Qi Fibonacci number. And here the constraints are Q is going to be less than 10 to the power 5, and we have the same boundary for n, and there's a limit of memory, like 120 megabytes max memory limit. So in this case, the program or the solution that you come up needs to be memory efficient so that you don't exceed this 128 MB memory limit, right? So here's the problem again. Now I want us to give a little try to solve this one. Okay, so let's try to come up with an algorithm that's going to allow us to solve for this scenario, and let's see how we can like we can see the different approaches that we can take and probably talk about what can we do to improve the memory efficiency of the algorithm that we come up with. Okay, so for this, let me share a link. Um, let's Okay, so I added a link to the chat. You can click on that link and then you'll be able to join an Excalibur board. Right, so we have the problem. And so now what I want us to do is to basically try solving this one. Okay, so any of you guys, you can try to come up with an algorithm. So let's take like 10 minutes and think about the problem and think of how you can solve this. So for the algorithm, you don't have to like go in depth about like writing pseudocode. You can just express in instructions like what you need to do, right? In plain English instructions, we can talk about the idea. And let's wait a couple of minutes and see what we can come up with. And for your solutions, if you can please like draw some rectangle and add your name, something, and then you can write down your algorithm or your approach within that box, so we're not colliding with the other people's ideas. And also let me share Excalibur. So let's wait until 7:05 and see what algorithms you come up with. Also bring in the algorithm that we had for computing the 21st Fibonacci number. Right, so it's here for you to see. And if you have any questions, please feel free to chat in the chat box, or you can unmute and talk. To kick things off, I also write some base case. Okay, so I see everybody just wandering around. Let's say What else do we have? Guys, let's write down some approaches. All right, I'm not seeing anything. Let's talk about the bottlenecks in this one. Okay, so this is the base version that I entered. What could be a problem in this one? So we have an input cube, right? Input array cube, which is going to be of size 10 to the power 5, right? So this is like 100,000 elements. And so we have 100,000 up to 100,000 queries. And for each one of those 100,000 queries, we're going to see an n, which is going to be between 1 and 1 billion. And so for each such qi, we're going to go through this whole process of computing or repeating a loop. Let's say if we get a 100,000 array of 1 billions as the input, you're going to call this Fibonacci function to compute the 1 billion Fibonacci number 100,000 times. And inside of our loop, what's going to happen is here. In here, we are going to loop 1 billion minus 2 times for each one of them. And that whole thing is going to get repeated 100,000 times. So like the number of operations that we'd execute is going to be 10 to the power 9 times 10 to the power 5, because 10 to the power 14. So this is computationally speaking, this is going to take a long time to execute. And we discussed that you need to come up with an algorithm that's going to terminate within given time limits, right? And in this case, this version is too slow. And so for your information, a benchmark or like for a 1 second algorithm, like one second time limit, or 5 second, like 1 to 5 seconds, or even for 10 seconds, what we're looking at is to have the number of operations under 10 to the power 9. Okay, so in a competition, if you get in at any place, if you want to determine the complexity of your solution, try to make sure that the number of operations that you do at the end is going to stay around 10 to the power 9. Okay, so that's the usual rule for CP competitions, especially the one that you're trying to getting ready to go the IEEE Extreme. And so to improve this, what are the ways that we can improve this? So one bottleneck that I'm seeing here is that for each and every query, we compute from the first Fibonacci number to the nth Fibonacci number. So what mechanisms could we use to improve this? And type your answers in the chat box or in the Excalibur board directly. Here I have one response. I want more responses. What do you think we can do? Okay, so what we could do is like in here, we are computing the same value again and again, right? So let's say I wanted to compute say 50 Fibonacci number. Our algorithm is going to compute the first one first, second, until 50th, right? And so this is for a single query. And for each and every query, say this one goes until 500, so it goes until 50,000, so on and so forth. So there could be queries that ask for the third Fibonacci number, or like when you're computing the 50,000 Fibonacci number, on your way you're also going to compute the 50th and the 500th, right? So what if instead of for each and every QI that we have here, first you take a look through Q and see what the maximum number is, right? And then what you do is compute from 1 to that maximum QI Fibonacci number, right? As you go through, we need to figure out a way where we can, let's say now we have an array of Q, right? So we have this array. Where we have different QI elements. And so one could be 1, this could be 2, this could be again 1, something like that. So as we are computing up to that QI max QI Fibonacci number, we can see as we compute a result, we can take a look at this array and see if we have any requests for that particular QI. And if there is, we can store the result in a parallel, another array that we have. Let's say this is results, this is Q, right? So if there's a way where we can, let's say, if when we are computing the ith Fibonacci number, we need a way to figure out if the I is here within any slot of the array here. And if it's present, then we can store the result in that particular ith box that we have on the corresponding results array. And once we are done processing through up until the max QI, then what we have is to basically print each and every element of this results array. Now there was a black box where we did not talk about how you can figure out if an ith element is there in this queue, right? And the way to do this is using what's called a hash map. And I hope you guys had a chance to talk about hash maps during the data structures that you discussed during the previous workshops. But if you did not, this is a data structure similar to an array where you can do queries like order 1 queries or like instantaneous constant time queries to look up for values within this map, right? So that's the way, like this is a mechanism where we are going to cache the results intelligently. So we only utilize memory in the size of Q instead of storing all the values from 1 up until QI, whichever it is, let's say 1 billion. Instead of storing all that huge array, what we do is we only store a subset of that corresponds to the result. So how this is going to differ from a version where we store, let's say, every possible result up until 10 to the power 9, and here we have 1. So this is a very big array versus this results array is going to be at max 10 to the power 5 in size, because in our input constraints, we were given that Q is going to be at max 10 to the power 5. Versus if we were to store this whole 10 to the power 9 array, it's going to consume quite a huge amount of memory in our case. So like if you were to store an integer array of 1 billion items, it's going to consume around 1 gigabyte of your memory. So that's a calculation that you can do actually and figure out what exactly that value is. But instead of caching all of those 1 billion elements, like in our worst case here for n, what we are doing is we are selectively storing the particular elements that only correspond to the results or the queries that we have. So this is an optimization that we can do, which is going to allow us to be efficient on memory, as well as in comparison to this version 1, it's also going to be efficient in terms of the runtime, because we are not going to execute this compute Fibonacci computation for each and every query. So that's how we would approach this problem here. Now, do you guys have any questions before we continue on from here? If you have any questions, post them on the chat box. Or if you got understood what I meant, you can do a thumbs up. So I know if you really got anything at all. All right, what is it? Do you guys have any questions or problems, or are we good to move forward? All right, so we're going to move forward to the next one. Let me share the presentation again. All right, so we were looking at building a memory efficient algorithm. And so we talked about building memory efficient and fast enough algorithms. How do you quantify when you come up with an algorithm, whether it's fast enough, whether it's memory efficient? And to quantify, we have a notation mechanism called the big O notation, or the worst case complexity analysis, which is going to give an indication about how your algorithm is going to perform in terms of the runtime as well as the space. So in a high level, like we have different complexity classes like order 1, order log n, order n, and log n squared, or a polynomial, and then we have exponential, and then we have factorial. So as we move forward, like go in this direction, what happens is whatever the value you have for n, the number of elements, as they increase, the number of operations, or operations, or in this case, the number of the size of storage that you're going to store in your application is going to increase. So in order 1 algorithm, it's going to be constant time or a constant space. That is, no matter how many elements that you have in the problem, you only consume a constant amount of space or time. A log n is not as good as a constant time, but it's going to consume only a log n time. So it's like if you had 1024 as n, it's going to do going by the base 2, it's going to do like 10 the value. And then we have linear time, then we have linear rhythmic time. So this n log n is for linear rhythmic. And then we have polynomial, exponential, and factorial. And so I hope you had some insight into this one during the previous sessions. If not, you can take a look at this link. I'll appreciate it if organizers could share the link of this one. So this is a book that I recommend you guys to read. It's called Competitive Programmer's Handbook. And this teaches you how you can compute the complexity of your algorithms, right? And so utilizing this, you can compute how complex the algorithm is and then determine if that algorithm is good enough to solve the particular problem. Now, moving on to the next step, how do you get better at competitive programming? So we took a look at what competitive programming is, and like we kind of broke down the different things, like the intricacies that you have in competitive programming competitions. And now we want to look at how you can get better at it, right? So first thing is that you need to be able to come up with algorithms that are correct, fast enough, and memory efficient in order to score, right? So one thing where you need to get better at is coming up with these algorithms. So when you want to come up, like when I mean coming up with algorithms, that does not have to be writing a pseudocode, right? It means that like in some way, like through your mind or by drawing or writing down the steps in some high level form, drawing diagrams or whatever it is, you need to be able to, when you see a problem, to come up with an algorithm that is going to be correct, and it's going to be fast enough, and it's going to be memory efficient to solve that problem. That's the first part. And once you build your thinking capacity to come up with such algorithms, then comes the next part where you need to build the ability to turn those algorithms into code, turn those ideas into code. So the second step is where you need to learn some programming languages. Like you can start with one, get better at it, and then, if possible, expand into a couple of programming languages as well, such that whenever you have an algorithm, you should be capable of turning that into code so that it can execute without running into compile time errors, and then like properly turn it into code so that we can submit the solution. And third thing is you need to do it very fast, because in a competitive programming environment, you have to come up with this whole thing, like solve the problem, turn it into code, and then you will submit it very fast, because very fast as in that's how you score better than other people. Typically in general competitive programming competitions. And so these are three areas that you usually need to try and optimize, right? So the second one, it's turning things into code. It's something that you're going to gain with practice, right? So as you solve more and more problems, you're going with a single programming language, you can learn ways to use like shortcuts available in that language to quickly and easily be able to turn your raw algorithms into code, right? And doing it fast is just going to come through experience, or as you do this on and on, because it's going to come through practice. It's and like in when you're practicing, you need to be very conscious about the time that you are spending, and then when you keep practicing and doing practice competitions, this will gradually become better. So we will focus put our focus in this one, because when you majority of the people, like they get stuck in this step itself without going into the second or the third one, right? Why I mean that is, usually for you to come up with an algorithm, the first step is you need to understand the problem, right? So before you start thinking about solutions, you need to analyze the problem and like figure out the edge cases that might be there. Like for example, in our Fibonacci series case, one insight that we got was, like, although you might have 10 to the power 5 100,000 queries, in each of those queries we might see repetitive things, right? So like when you want to compute the 100,000th Fibonacci number, and if you want to compute the 50th Fibonacci number, along your way to computing the 100,000th number, you might also have to compute the 50th, right? So that was an insight that we figured out while analyzing the problem and how you have to compute the Fibonacci number using the recurrent formula that you have for Fibonacci series. And so when you get a problem, you need to figure out the edge cases that you might have, because for your algorithm to be right, you also need to be able to ensure that that algorithm covers the edge cases in solution space, right? So this is very important because in CP competitions, you need to create correct algorithms, right? So if your algorithm is not right, then you're not going to score at all. In some competitions, there are partial scores, but majority of the time, problem setters try to ensure that the solutions submitted are correct. So you need to figure out those edge cases and make sure that your algorithm is going to cover, like, provide proper answers for the edge cases. And third thing is, when you have a like huge problem, you need to figure out a way about how you can break this problem down into sub problems, right? Sub problems in the sense to smaller pieces that you can then relate with some form of algorithm or data structures or standard techniques that you have learned. So you can gradually, when you combine this together, it's going to end up solving the problem. So these three are very critical when you're competing competitive programming competitions, and majority of the people, even before they get into this stage, like even before they run into limitations in writing code, they hit this limit. Majority of the people, right? So people say that, like, when you understand a problem well enough, it's a problem half solved, right? Because before you jump into a solution, you need to, if you understand what the problem really is, then you're going to come up with the correct solution. And in CP, it's really important, because if your algorithm or the solution is not correct, you're not going to score. And so the second part is coming up with an algorithm is, once you break this down, once you break down a problem into sub problems, then you need to identify the relevant data structures or algorithms. Or these algorithms do not have to be very complex algorithms, right? This could be like, how do I add two numbers, or how do I find the maximum in three numbers, or from an array of n numbers, or how do I find the median of that? Like the complexity of the algorithms that you know from memory is going to vary based on the exposure that you had in competitive programming, right? And so when you're a beginner, what you would know are the basic like algorithmic concepts, like how you can recurse, how you can write loops, how you can utilize the memory to do caching, and maybe you might have learned about dynamic programming or greedy algorithms, etc. Right? So the next part, this part is where, once you can break down a problem into sub problems, your ability to identify which or relevant data structures or the algorithms or the modified algorithms that are needed to solve the particular sub problems is the next skill that you need to develop. And so these two goes hand in hand, right? So like how you break down a problem into sub problems is also going to depend on what knowledge you have about data structures and algorithms. And like from a very primitive data structures like arrays or variables up to very complex ones. It's all going to depend on how good you can utilize them. Right. So once you get better at this, right? This is usually the first place people get stuck, majority of the people. And then where you need to optimize is being your ability of turning this into code. And being majority of you guys being CS students, I hope a lot of you can write down decent code. So first try to optimize this part, right? And as you do this, you'll automatically get better at this because you will have to do a ton of practice problems. All right. So from this section, do you have any questions? It looks like that. Good. So, like I mentioned previously, the algorithms and data structures, they don't have to be like very complex structures, right? You can start with knowing just arrays or variables. And on the other side, with algorithms, you could know like how you could add or how you can write recursive functions. But from that point, you need to gradually build up your knowledge base, like to learn about some complex algorithms and data structures, because throughout the years, people have identified some common patterns that are there in writing algorithms. So like dynamic programming, greedy algorithms, two pointers, line sweep, bitwise operations, game theory, graph theory. There's a ton of areas that have very standard algorithms, right? But before learning those algorithms, like you will know like a small subset of algorithms that you're already familiar with. You need to build your ability to identify the right data structures and algorithms from the list that you know to a problem, and like being able to apply those mechanisms to solve the problems that you're facing. So that's a core ability that you need to fix, because it does not matter if you know a ton of algorithms unless you can figure out a way about how you can map a certain algorithm to a given subproblem. Let's say you should know how you can when to use spanning trees to solve a particular subproblem in a whole big problem, or how you need to modify a standard spanning tree algorithm in order to fit a problem, right? So that's an ability that you need to earn or learn by practicing. And same goes for data structures, right? Uh, there are tons of data structures, and so start with what you know right now. And I would recommend you to, again, read this book. Put this on chat. So this is called the Competitive Programmer's Handbook. And it's really good. It covers a really good basis about algorithms as well as data structures that you might want to know to compete in competitive programming competitions. But like I said, start right now, like start practicing, and as you go forward, learn more and more algorithms and data structures and keep progressing forward. And so this is that book again, and this is another YouTube channel that I would recommend. So if you have some time, so this is channel where this guy, and there are many channels right now. So Eric To is a person who's been a competitive programmer for quite a long time, and a very talented one at that. And so you can, like, this is similar to like watching gameplays, where you look at people solving problems, and you can look at how they think and learn those ways yourself, right? That's one. And then the next thing is like the main component that we talked about was discussed was you need to practice. So these are two resources that I would recommend. So one is Code Forces. The second one is this Academy. So Code Forces, it has competitions, I think, every week. Like you can compete in a 2 hour competition. And so this will really help you to polish up your competitive programming skills, because like this is going to be a timed competition, and there's a ton of competition in this context, right? So like hundreds of thousands of people come and compete. And CS Academy, I wanted to highlight this here because IEEE Extreme is getting hosted in CS Academy. So you'll be able to find out some of the past problems of IEEE Extreme through CS Academy. And so it's a good place to practice like past problems of IEEE Extreme or just problems. And this is a good place to practice competitive programming, real live competitive programming competitions. Okay, moving on. So we are that concludes the general portion about like getting better at competitive programming. And now we are going to focus a bit about specifically into IEEE Extreme because at the end of this CodeRally workshop series and the hackathons, you are trying to go and compete at IEEE Extreme, right? So preparing is actually like you need to learn the theories and it's a whole lot of practice, right? So up until now, what we discussed was only the basics or like in any general competitive programming competition, what's involved. But with IEEE Extreme, it's a team competition. So there's a different set of dynamics at play at IEEE Extreme because it's not only that you need to be able to come up with algorithms, but you also need to build some ability to communicate that algorithm to your teammates, right? To build an ability to discuss and come up with solution faster because a way to get faster at CP competition and in this case at IEEE Extreme is to one thing like when you have three people could be looking at three problems at three different problems, or you could have like multiple people discussing the same problem to come up with an algorithm to solve that particular problem in order to cut down the time that you have to spend on the problem, right? So in order to do that, you need to practice with your team to build that dynamic, to build that team dynamic, right? So up until IEEE Extreme, how you can prepare is to basically learn the theories and practice with your team. So I would recommend if you can compete in code forces and like once a week you can. These competitions are like 2 hours, right? If you can dedicate 2 hours a week, you can practice taking those problems with your team. And at the competition, IEEE Extreme, the competition is a 24-hour long competition, so it's a marathon, right? So don't waste all of your energy at the beginning of the competition because you need to stay up for 24 hours because at IEEE Extreme, they don't publish all the questions at the beginning. So like every hour, you're going to see 2 or 3 new questions. So you need to be able to keep up and during the last couple of hours, the competition is going to be really tight. If you are going to look for a position or a rank, because people keep submitting and submitting, like doing really minute fixes and going up, which I will focus here. So going back, like it's a marathon, so don't waste all of your energy and get a good sleep on the previous day. And you need to have some mechanism that's going to allow you to stay awake and stay sane during that 24-hour period because your brain needs to be in a good condition to solve the problems. And that's about IEEE Extreme being 24 hours long. And the second one is that IEEE Extreme, at the competition, you don't get bonus scores for submitting a solution fast, right? It does not matter if you, let's say you consider a single problem, it does not matter if if you submit it at the beginning of the competition or at the very end of the competition. You and the other teams get the same mark, right? So what this means is that if you see a problem that's hard or you can't see a way to solve that problem, leave it for now, right? Leave it and start tackling a different problem. Or if there are no problems, have a rest and try to get a refreshed mind so that you can start looking at the problem from a different angle. And again, I want to emphasize like don't think about solutions, right? Try to understand what the problem is and try to analyze the problem and break it down into sub problems so you can then solve those sub problems individually. So that's very important. And then the third point is IEEE Extreme, it allows partial scores, right? So previously we talked about an algorithm that an algorithm needs to be correct but an advantage that you have at IEEE Extreme is that even the algorithms that are not so great can get scores because they have partial scores, and the test cases are not that super like tight. They are not very tight in a way that they can evaluate for the correctness of the algorithm. So you can utilize partial scores to uh, boost your rank up. Okay, especially during the last portion of the competition, you can move a couple of places up or down by collecting these partial scores, right? And then the final one I want to say is like, don't stick to a single programming language. So this is specific to IEEE Extreme, okay? Because at the competition, you usually like get some problems that can be solved fairly easily using certain types of programming languages versus using some other languages. So have some flexibility around it. Like you could have a primary programming language that you're going to use to code. And for example, in my team, I used to code with C++, and my partners used to code with Python. And so each of us had our primary programming language, but we also competed in using other programming languages if needed. So choose the language based on the problem, like if there's any benefit. So those are the tips that I would say for that you need to keep in mind and for competing at IEEE Extreme specifically. And so that concludes the items that I wanted to share with you guys. Now we can move into questions. If you have anything, any problems that you've been having throughout the days or the couple of months or the weeks. Yeah, and so if you can, please unmute and speak. Otherwise, type them on the chat box. So let's spend around 5 minutes. And yeah. Right, until that's coming, I also have some homework for you guys if you are interested. So this is a problem that I'd like you guys to try out. So there are two sorted integer arrays, A and B, right? The problem is you need to find the median of the two arrays combined. So you have two independent arrays that are sorted. You combine those two together, and now you need to find the median of the array, median of the combined array. And for the constraints, we have the length of A and B given, like they are going to be between 1 and 10 to the power 12. So in this one, you need to consider about like building a time like an algorithm that is in terms of the time complexity that is efficient enough that you can figure out what the median is without spending all the time. And for the sake of like coming up with a solution, assume that for this one you have unlimited memory. Okay, so because 10 to the power 12 is very high. Right, we have one question. I joined the meeting a few minutes ago. Can I get the recording? I hope you can. The organizers, could you speak whether it's possible? All right, then think we are good on the questions as well. We don't have any questions coming up. And that concludes what I had prepared to present to you guys. I hope you learned something today during the last hour. So thank you very much for joining in. Yeah, Pasindu, back to you.
Yes. Thank you, Mr. Pasindu Wijesena, for sharing your expertise and guiding us. We would like to take a moment to express our heartfelt gratitude to our speaker, Mr. Pasindu Wijesena. Your time and effort in leading our final workshop at CodeRally 5.0 on tips and tricks for computing programming are greatly appreciated. Thank you for sharing your invaluable knowledge and expertise with us. And now, we're glad to announce the winners of the SWAG Challenge. Congratulations to Devmit Magamage and Chamot Pankaj, our standout winners of the SWAG Challenge from Workshop 5. Your effort and creativity have truly paid off. Your prizes will be given at our hackathon event or contact our delegate vice chair to collect your prize. And we are also thrilled to announce that our CodeRally merchandise is now available. You can purchase your favorite bundle from the link in the chat. Don't wait, hurry up and grab your merch. Last but not least, let's acknowledge our valuable title partner, eFutures, who has been with us since the beginning of CodeRally 5.0, providing great support. To capture the lively spirit of our community, let's take a quick group photo. Please turn on your cameras and smile for the picture. Thank you once again for joining us today. We look forward to seeing you at the hackathon of CodeRally 5.0. Have a great day.